Welcome to the journey of silicon innovation at AWS. My name is Ali Saidi. I'm a senior principal engineer and the lead engineer for our Graviton2 based instances. Today, I'm going to talk about why we're building our own chips in AWS. And really, it's about customers. Building our own chips lets us innovate on behalf of customers faster, raise the bar in security, and deliver more value. There are three areas where we're invested in building our own chips. The first, the AWS Nitro System, where we've moved functionality from a traditional hypervisor onto purpose-built chips we've built in AWS. The second, AWS Inferentia, a chip for machine learning inference. And the last one, AWS Graviton, host processors that deliver the best price performance. I'm going to talk about each of them in turn, but first, I'm going to spend a little more time about why we build our own chips. AWS is the only provider that's built chips that span the breadth of I/O, machine learning, and host compute. Why do we do it? To improve our customers' experience and deliver them higher performance and more efficient solutions. Building our own chips lets us have better time to market, higher security, and better reliability. And we can build chips from the ground up for our use cases, which means we can focus on the features that provide value to you, and we don't have to spend time and resources on features that we're not going to use. Developing our own chips also means that we own the end-to-end development process, including when we start the project and when we deliver it. This lets us bring technology to market sooner. And we also get to take our software and our hardware teams and have them work together from day one on the best solution. When you have a team developing the silicon, the software, the hypervisor, the I/O devices, all under one roof, there's faster innovation, there's easier time debugging, there's cross-cutting quality. The last is operationally. We can bake in features into our chips that let us do things like live update the firmware that's running on them without disrupting the customer experience, that leads to higher reliability. Let's take a minute now to look at what a more traditional compute environment looks like, and then we'll compare it to what we're building today in order to improve our customer experience. So if we start with a typical server, at the heart of that server is a processor, typically from Intel or AMD. And that processor needs some storage. In this case, I'm showing you NVMe, and some networking. Perhaps there's a GPU or some other kind of accelerator. At AWS, we're innovating across all the devices I've shown you here to raise the bar in security, enable higher performance, higher availability, and provide you with more value. The traditional I/O cards I showed you in the previous picture, we've replaced with our Nitro cards. These provide higher performance I/O than would otherwise be possible. Nitros also let us raise the bar in security with a Nitro security chip that protects critical motherboard resources. We also have Nitro cards that do things like encrypt everything you write to local storage with an ephemeral key that's destroyed when the instances are terminated. We've been investing in AWS Inferentia, custom silicon designed to accelerate machine learning inference and lower the cost of you using machine learning in your applications. And finally, while we've had processors from Intel since the beginning of EC2 and AMD from several years ago, we're also building our own processors, which provide 40% better price performance and increased efficiency. Let me start by diving into AWS Nitro. Nitro is a fundamental rethinking of how virtualization is done and was the first place that we invested in custom chips. It let us provide higher performance to customers, raise the bar in security, and rapidly deliver new instance types. The Nitro project began with a simple question of, after building EC2 for almost a decade, what learnings could we take from the aspects of the physical platform, the large number of hosts we had, and looking across the hardware and software boundary? This ultimately led to Nitro, and we introduced Nitro back in 2017 with the C5 instance. But while we introduced it in 2017, we had been working on some aspects of it since 2013, when we introduced enhanced networking in our C3 instances and moved some of the traditional functions found in a hypervisor. That's the piece of software that takes one server and partitions it into multiple virtual machines, and moved some of that functionality from that hypervisor into purpose-built hardware and software. This let us simplify the hypervisor, and ultimately we replaced the hypervisor we had been using with one of our own, based on Linux and KVM. Since 2017, all new instances that we've launched have been based on the Nitro system. So if you've been using a C5, M5, or R5, an M5A or R5A, or a C6G or M6G or R6G, you've been using the Nitro system. The Nitro system is composed of three important but independent blocks. The first is the Nitro Hypervisor. This is a lightweight hypervisor that just focuses on memory and CPU allocation, and ultimately provides bare metal-like performance. Prior to Nitro, we used a hypervisor called Zen. Zen's great, but it also did a lot. It did memory and CPU allocation, but it also did device emulation, logging, monitoring, and has a full-blown Linux user space. All of this uses resources on the host CPU, and we looked for ways to simplify that. We moved most of the functionality off of the host, and we're left with a simple hypervisor that just focused on memory and resource partitioning, without any full-blown Linux user space. So where did that functionality go? Some of it went to the Nitro security chip. And security is the most important thing we do in AWS. And since it's such a priority for us, it's the first thing we think of when we start building something. When we decided to build Nitro, we tried to determine, was there more we could do from a security point of view? And that led to the development of the Nitro security chip. This purpose-built chip takes security functions away from a vulnerable place, the host CPU, and runs them on a dedicated piece of silicon. This reduces the attack surface, mitigates against many threats, and provides us a root of trust in hardware. So I mentioned that the I/O responsibility was removed from the hypervisor, largely. Where did it go? Well, it went to the Nitro cards, which are our I/O accelerators. Each card has a chip that we developed internally in AWS. We don't necessarily have just a single card, but we've got cards that create the VPC networking that you've experienced, in EBS, instance storage, and also system control functionalities. And by moving the functionality there, we were able to drive better performance than was possible with the hypervisor-based solutions, as well as keeping all the resources on the host available to our customers. I only have time to dig into one of the cards, so I'm going to talk about the Nitro card for Amazon VPC. This is the card that interacts with the ENA device driver you might know about in your virtual machines. The ENA device driver is available for all major operating systems, for x86 and for ARM. And one of the cool things about it is it's independent of Fabric. We've gone from offering 10 gigabit to 25 gigabit and now to 100 gigabit networking, and done that independent of Fabric. So you didn't have to change your drivers to get that higher performance, which is pretty unique actually. Usually when you get that kind of performance delta, you have to go and change your drivers as well. The card itself and the chip on it offloads the functionality of the Amazon data plane. This includes encapsulating your packets onto your VPC, enforcing security groups, limiters, and routing, and it's all done on the card to be as close to the server as possible and have the lowest latency. Having this functionality outside allows us of a hypervisor allows us to have bare metal instances, including the new EC2 macOS instance and our other metal instances. And we've also extended this functionality beyond just ENA to the Elastic Fabric adapter and provide high-performance networking for HPC, MPI, and machine learning workloads. I mentioned that the Nitro hypervisor was lightweight, and that means it reduces jitter. Customers with applications might need to react to a timer or to a network packet, and they care about how long it takes for them to react to that event. In this graph, I'm showing the time after a virtual machine wanted to wake up that it was able to. And I'm plotting all the samples here as a probability density function. C4 was our last instance before Nitro. We worked really hard to reduce the jitter and wake up delay here. But you can see the bulk of the responses are between 70 and 170 microseconds. And there's actually tails that go out all the way to 1,000 microseconds. With C5 and the Nitro hypervisor, you can see two things happened. One, the distribution tightened a lot. And two, it moved far to the left. This is really the power of the Nitro hypervisor, reducing the wake-up delay and jitter in our systems. With our Graviton2 based C6G instances, the same is true, except the distribution is tightened even further, and we've moved it even further to the left. Not only has Nitro had a major impact on security and performance, but also on scale. Nitro has allowed us to accelerate the pace of innovation. It took us 11 years in EC2 to go from 1 instance to 70, but in 2017, something happened. In just 3 years, we've gone from 70 to over 350 instances. And that something was AWS Nitro going to production. That rapid innovation for you means greater choice of compute, networking, and storage, so you can better tailor the resources of the cloud to optimize your workloads in both performance and in cost, and quickly scale as your business grows. Now, I'm going to switch gears a little bit and talk about machine learning, and share with you an overview of our Inferentia chip, which is an easy-to-use, high-performance machine learning chip. It enables customers to improve their application quality with state-of-the-art models at an affordable price. While training chips have received a lot of attention, in reality, many orders of magnitude more inference occur. In fact, based on our internal usage, the majority of the operational costs of running machine learning comes from inferencing. Inferentia enables high-performance, low-cost machine learning inference in the cloud. Each Inferentia chip can provide 128 teraops of performance, and the vertical integration in AWS allowed us to design Inferentia and the server it was going to fit in together. We put 16 Inferentia chips together in a single server that delivers over 2 petaops. This is more than double the performance of our P3 GPUs. The chip also implements a large on-chip cache so that we're able to run models from the cache. And that cache, combined with our interconnect technology between chips, allows us to connect multiple Inferentia together into a larger virtual device and pipeline inferences across it. This functionality allows Inferentia to reduce the latency of inference by as much as a half compared to GPU instances, while keeping the throughput the same or better. As I mentioned earlier, when we start a project that involves silicon, we also start the software for at the same time. And this was no different. We started investing in the Neuron compiler for Inferentia when we started building the chip. And that partnership between the software and the hardware, and the chip and the compiler, means the effective utilization of Inferentia is higher than you see in a GPU, and that leads to better price performance. Inferentia is supported in popular frameworks such as PyTorch and TensorFlow, and is usable directly in virtual machines or containers or through managed services like SageMaker. Another factor that let us reduce the cost of Inferentia is the performance per watt efficiency, which is around 2x better than that of GPUs. Here I'm showing you over a 2-hour run, second-long measurements of performance and power measurements of a G4 or an Inf1 instance. And you can see that there's a range between 3 and 1.6x better efficiency, with the median being a little bit over 2. So let's talk about some customers who are actually using it. Simple ML models can run on CPUs, but as ML science improves, models grow in size, and that makes it prohibitive for many customers. Also, large models mean more compute, which can be a real problem for real-time services, like search or voice assistants. Inferentia is particularly compelling to customers who run into these issues: massive amounts of inference calls and tight latency budgets. We see customers like Snap running recommendation engines, customers that deal with massive amounts of text like CONDÉ NAST, or who have high-performance computer vision models like SKYWATCH, also using Inferentia. And we're proud that people within Amazon are also using it, including Amazon Rekognition and, of course, Alexa. As I'm sure you're aware, this is an Alexa device. And when you ask Alexa a question, a textual response is generated by Alexa's text-to-speech service. It synthesizes that speech so you can hear it. Text-to-speech is a very large compute-heavy service, and it's got a strict latency guarantee so that the customer experience is natural. You don't want a long pause after you ask your question. Inferentia fits this workload great, and the Alexa team has adopted Inferentia. So how did it turn out for them? Here I'm comparing Alexa's text-to-speech service running on a P3 instance, which is the instance type they used to use, to an Inferentia-based Inf1 instance. The first thing you notice, it's 30% cheaper. But that's not all. It's also 25% lower latency. By using the on-chip cache in Inferentia, the Alexa team was able to reduce their application latency by 25%. This is critical because it allows the team to experiment with more compute-heavy models and continue to improve Alexa voice. And I'm going to change gears one more time now and talk about AWS Graviton. Graviton are purpose-built chips for host compute that are available exclusively in AWS. They provide the best performance and price performance in their instance families, so we're going to dive in and talk about what they offer. ARM processors are ubiquitous around us, For years, they've powered the phones and tablets we use every day. They're also starting to show up in laptops and with Graviton2 servers. Our Graviton processors have targeted optimizations to reduce costs and power consumption, which means they're less expensive to operate. We're on our second generation of Graviton processors now. We announced the first one back in reInvent in 2018, and a year later in 2019, the second. The second generation increased the core count by 4x, the performance by over 7x, and the performance per vCPU by around 2x. In a single generation, these are massive numbers. Today, Graviton instances are used in 8 instance types in an ever-increasing number of regions. And they use those Nitro building blocks that I described at the beginning of the talk. We designed Graviton2 to provide the best value for our customers. It's powered by ARM Neoverse N1 cores, and we work closely with ARM on the development of that core. It's a large chip with around 30 billion transistors. The end-to-end ownership in AWS of the design and development of Graviton meant that we only had to build the functionality we needed. We could test that really early in the design process, and we could deliver that functionality in a fraction of time of the incumbents. When we built Graviton2, we wanted to provide consistent performance across all the vCPUs. It's also 20% less expensive than an equivalent C5, M5, or R5 instance. And it's also 3x more efficient in terms of performance per watt than an equivalent R5 instance. That means it's greener, less expensive to operate, and you can see that reflected in the costs. So now I'm going to talk a bit about some of the functionality that makes Graviton2 perform. But to do that, I need to start with how an x86 processor works. The processor core is what fetches, decodes, and executes instructions. For example, if you have an add instruction, that's where it gets executed, and R1 plus R2 is equal to R3. To make processors fast, there are caches. These caches hold copies of data close to the processor. The L1 cache can be accessed in a couple cycles, the L2 in around 10, the L3 in tens of nanoseconds typically, and memory closer to 100 nanoseconds. These cores have gotten pretty big, and to improve efficiency on x86, multiple threads have been added. By threads here, I don't mean operating system level threads. I mean simultaneous multi-threading or hyper-threading. These individual threads look like CPUs to the operating system. Now, the upside to the threads is they improve performance and efficiency, but the downside is they contend for resources in the cache. For example, there's only one divider, so if both threads want to divide, one of them has to wait. With Graviton2, every vCPU is a core. There aren't any hardware-level threads, and each CPU is smaller and more efficient, so you can pack 2 times the number of them into a chip. This provides better scalability, as the core, the L1, the L2 aren't shared. There's been a whole class of security issues we've seen over the last 2 years with multi-threading that doesn't apply to Graviton simply because Graviton doesn't have multiple threads. Beyond that, the core in Graviton has been optimized for server workloads. As I mentioned earlier, ARM is hugely popular in tablets and cell phones, but those aren't a server. While a modern web browser or Node.js application might look similar in a lot of ways, the server is doing orders of magnitude more context switches, more system calls, and instead of running no VMs or maybe 1 or 2, it's potentially running hundreds. With Graviton2 and the Neoverse N1, the latency of these operations were reduced significantly from what we've seen in previous systems. Caches are one of those things that make the processor fast. And because there aren't threads in Graviton2, it means per vCPU, there's a lot more cache. While the absolute sizes you see here on the screen are similar, in Graviton2 they aren't shared. So we have 4 times the L1 cache per vCPU and 2 times the L2 cache. So we've got these cores. We have no threads, we've got big caches, they've been optimized for server workloads. Now we have to put more than one of them together. If I could lift the lid off the picture I showed you a few slides ago, you'd see this. The black square in the middle, that's the silicon that contains 30 billion transistors. In there, we've got 64 cores. Connecting them is a nearly 2 terabyte a second mesh. All the cores are placed close together, so if they're sharing data or working on a problem, they can communicate with each other quickly. Embedded in that mesh is a 32 megabyte last level cache. And between that cache and the cache in the cores, there's over 100 megabytes of user-accessible cache on the processor. We've got a lot of flexibility for different instance types with 64 lanes of PCIe. and over 200 gigabytes a second of theoretical memory bandwidth from 8 DDR4 3200 channels. The cool thing about this here is it's really easily accessible memory bandwidth. Simple loops extract 83% of the theoretical memory bandwidth, compared to other systems, which are typically in their 60s or even lower. One thing you'll see is missing here, there's no multi-socket. Why? We don't actually think most people need it. It leads to NUMA issues, scale and scalability problems. NUMA stands for non-uniform memory access. It really asks the question, is the path from the cores to memory the same or different? Is there near memory and far memory? Few people know what it is. Fewer still even write software for it, and most people just rely on the operating system to handle it. But the operating system has really imperfect information. It doesn't know the sharing pattern in your applications, so it doesn't know where it should allocate that memory. We get rid of these problems by having all the cores together on one die, as you see here. So how does it perform? I've got several examples of benchmarks comparing Graviton2's M6G to the previous M5 instance. And in a few slides I'll also talk about what some of our customers have seen. But there's no substitution for running your own workload. So please try your own workload on Graviton as opposed to a micro benchmark. So first I'm showing SpecInt 2017. SpecInt is a collection of CPU-intensive workloads that do things like compiling code, route planning, XML to HTML conversion, Sudoku solvers, and others. Here, we're showing 44% more performance per vCPU on an M6G that's Graviton2 based versus an M5. Next, we have Nginx. Nginx is a popular web server and load balancer. Here we've configured it as a load balancer and have a load generator that's simulating over 500 clients with HTTPS and load balancing between 4 backend servers. Here, the M6G can push 24% more requests per second than an M5. And finally, I have Memcached. Memcached is a popular key value store. Here, we've got a couple load generators using 16-byte keys and 128-byte values. You use Memcached because you want to improve your application responsiveness. And so here you can see that the M6G is able to provide 43% more requests per second relative to an M5. But the other cool thing that I don't have time to show you is the latency versus throughput curve. If I could show you that, you'd see that throughout increasing throughput, the M6G latency is better, which is exactly what you want in a key value store. So it's fast. How much power does it use? In a typical mainstream server, the single largest consumer of power is the CPU. How does Graviton2 stack up? It's actually the most efficient CPU we have. More in terms of performance per watt versus like an R5 instance, as I'm showing here. It's 3x higher performance per watt. And since we always look to pass cost savings on, this what it means for our customers is lower cost, because the lower power consumption means lower operational cost. We can put more servers in a physical space, and it has a lower impact on the environment. So we've got 8 instances that are powered by Graviton2 that range from a 1 vCPU medium up to a 16 vCPU 16x large. They typically have more networking and storage performance than our 5th generation instances. We've got an M6G with 4 gigabytes of RAM for every vCPU, an R6G with 8 gigabytes of RAM per vCPU, and a C6G with 2 gigabytes of RAM. Additionally, for the C6G, M6G, and R6G, there are also disk variants that have up to 2 terabytes of instance storage. A burstable instance, T4G, is also available, and there's a free trial through March 31st, 2021. And this year at reInvent, we're introducing C6GN, a version of C6G with 100 gigabit networking. So as I showed you in the previous results, we have the highest performing instances in their instance families. They're 20% lower cost than our Intel-based 5th generation instances. One of the reasons for that is the power savings I just mentioned. And together that drives up to 40% better price performance versus comparable instances. Now I'm happy to say this isn't just our data. There are other customers who have seen those levels of improvement in their costs. I'm going to start with one, Lyft. Lyft's a transportation company. They have compute-intensive Python and Go-based services that are a major factor in the cost of their platform. They benchmarked moving from a C6G, from a C5 to a C6G, and found 30% better price performance, and commented that moving from C5 to C6G was reasonably straightforward, and they're looking forward to running the majority of their service fleet on C6G. Nextroll is a marketing platform that has Erlang, Go, and Java workloads, and between the improved performance of C6G and M6G and the lower cost, they observed a 50% cost savings by migrating to Graviton2. And they plan to move everything they can to Graviton2 in the future. SmugMug is a photo sharing website. They have a PHP-based photo serving app that runs on Graviton2 based M6Gs and C6Gs. And they saw 40% better price performance by just recompiling it. They report that it required minimal code changes for them to do that, and that it was actually simpler than upgrading their operating system. And lastly, Snap. Snap uses Amazon's Elastic Kubernetes Service, or EKS, to run in their messaging core service. They are using Graviton2 instances, and they're able to both reduce the cost of the the size of the messaging fleet, and also, because of the lower cost of Graviton2, significantly lower their costs, and are looking to move more workloads to Graviton in the future. There are more stories like this at our website, and you can see the URL on the screen. So, just wrapping up. Thank you for taking the time with me today as we walked through AWS's journey so far in building custom chips for EC2. Today was a brief overview highlighting some of the innovations in silicon at AWS that we've developed. It's still the early part of the journey, and we look forward to continuing it with you. I look forward to meeting you again in the future to talk about our continued progress in building chips to improve performance, security, system reliability, and ultimately allow you to spend more of your time innovating. Thank you, and have a great day.